All right, let's jump right into this explainer and completely decode the ultimate autonomous rescue challenge. Today, we're going to visualize exactly what it takes to fly a cutting-edge drone through an absolute gauntlet of disaster scenarios. This isn't just theory, folks. We are mapping the actual real-world flight paths, the takeoffs, and the incredibly complex landing sequences these machines literally have to conquer to prove they can save lives. Now, you might be wondering, why does this matter so much? Well, let's look at the human stakes. Emergency responders face absolutely grueling logistics out there in harsh terrain. As this quote hits the nail on the head, moving just one injured person a single mile out of the woods can take 20 people carrying a litter. 20 people! But these autonomous flyers, they're aiming to completely flip the script, turning hours of perilous, exhausting extraction into just minutes of precise flight. Think of this as your mission dossier. We're going to quickly cover first, the GoAERO Rescue Challenge. Second, productivity and the 1 mile ferry. Third, adversity and extreme landings. Fourth, maneuvering through the obstacle slalom. And finally, what it takes to actually win the final fly-off.
Okay, Section 1, the GoAERO Rescue Challenge.
Before we even map the skies, we really need to understand the strict physical constraints placed on every single aircraft stepping onto the tarmac. First off, every vehicle attempting these courses has to be completely uncrewed, no pilots on board. And they're run by a maximum of just 2 people on the ground for the entire deployment and operation. The primary payload? A 125-pound mannequin named Alex, who, thankfully won't be complaining about the turbulence. And crucially, you can't just show up and hope for the best. Teams actually have to prove their flight worthiness with a controlled, full payload validation flight 30 days before the event even starts.
Moving right along to Section 2, productivity and the 1 mile ferry.
So this first major mission is a seriously grueling 90-minute test of rapid deployment and endless endurance. It's designed to see just how much weight a drone can ferry into a disaster zone. But get this, the mission actually begins on the ground. The clock starts ticking the literal second a team's highway legal transport vehicle rolls into the operation zone. From there, teams have a super tight 30-minute window to conduct a completely tool-free deployment of their aircraft. Once they finally achieve liftoff, that 90-minute flight phase kicks in, and man, this is where the flight path gets really intense. Once it's airborne, the aircraft basically transforms into a high-speed cargo ferry. But we're not talking neat, easy-to-stack cargo here. They have to carry some really diverse, awkward payloads. They might load up Alex, the 125-pound mannequin, or these incredibly awkward 6-foot links of rebar, or even these 40-pound sandbags that intentionally have 0 handles. Yeah, no handles, making them an absolute nightmare for the ground crew to load up. And this setup brilliantly illustrates the absolute grind of the mission. The flight path actually forces the aircraft to constantly alternate. So they take off, fly a 1 mile out and back segment totally empty, and land. Then they load up the payload, take off again, fly that exact same 1 mile out and back segment fully loaded, land, gently unload, and repeat the whole shebang. The ultimate goal? To haul a massive minimum of 1,250 pounds before that 90-minute timer expires. It is just a relentless, continuous cycle of takeoffs, straight-line distance flying, and precision landings.
All right, Section 3, adversity and extreme takeoffs and landings.
Now, if that last section was all about endurance and distance, this one is all about surviving pure, unpredictable environmental chaos. Seriously, forget nice, clean helipads. Just look at the diverse threats these UAVs face the second they try to land. They have to stick a landing in the pit, which is a 12 by 12-foot zone of loose, dry sand that will just whip up instantly in the rotor wash. They have to land on a 12-degree carpeted incline. They even have to descend into something called the flood, which is an 18-inch pool with simulated rain where they literally have to momentarily touch a floating balloon. On top of that, they have to fight uncooperative wind shears in the tornado generated by heavy wind machines. And if that wasn't enough, there's the unknown, where blind obstacles up to 3 feet tall are just scattered randomly right across the landing zone.
This spatial path for this is just exhausting to even think about. The aircraft takes off from its base, carrying Alex. It has to hit an altitude marker at least 30 feet up in the air, then traverse over to a hazard zone and descend straight into the chaos. And once they finally touch down, well, they aren't done. They actually have to survive a brutal 2-minute ground pause, just sitting there taking a beating in the sand or the rain or the wind, before taking off and doing it all over again for the very next zone.
And the pressure is seriously on. Teams have exactly 30 minutes on the clock to complete this entire grueling sequence. That means navigating through all 5 of those wildly diverse, hostile hazard zones safely before the timer runs out.
Which brings us to Section 4, Maneuvering and the Obstacle Slalom.
This is really the climax of the flight profiles. If the last section was all about the environment, this one is a truly claustrophobic test of pure spatial agility. We really have to ask the critical question here. What actually happens when a drone descends into a cramped urban-like canyon where its GPS signals are intentionally scrambled? Because, real-world rescues don't always happen in wide-open fields. They happen in tight alleyways and blocked building corridors.
So welcome to the spot. Look at this setup. It's wild. It's a tiny 8x8-foot pad, and the only way in is through a gate totally blocked by stacked steel shipping containers. These containers are specifically placed to block the sky, degrade GPS and global satellite signals, and bounce whatever signals remain all over the place to thoroughly confuse the drone's sensors. The aircraft is totally forced to rely on its own advanced, onboard, non-GPS vision systems to stick a completely perfect spot landing.
Let's actually trace the exact flight path for a second because it's a completely dizzying weave. They take off with Alex. Then they have to navigate this crazy slalom, making a left turn above 50 feet for the first obstacle, dipping way down below 35 feet for a right turn on the second, popping up and hopping over a 50-foot virtual wall for the third, and then making another super tight right turn for the fourth. After all that, they have to thread the needle right into the spot, unload Alex, take off again, and fly the entire slalom course in reverse.
The contrast here is just staggering. Navigating this dense, varying altitude path with a full 125-pound payload totally changes the flight dynamics. Then, flying it empty immediately after requires completely different power management. Having to trace the exact same complex flight path forwards and then backwards, both loaded and unloaded, it perfectly highlights the absolute extreme precision these autonomous systems must possess to succeed.
Finally, Section 5, Winning the Final Fly-Off.
So, after mapping all these incredibly grueling flight paths, from the 1-mile ferries to the literal tornadoes to the GPS-denied slaloms, how does a team actually take home the $1 million top prize? Well, earning the top prize requires an aggregate score, and it's a very delicate balancing act. You get base completion points just for surviving the missions. But then you need rank points, which measure your sheer speed in your payload-to-weight ratio. Finally, there are bonus points, and this is totally vital. You get highly rewarded for true autonomy. That means doing all of this with minimal human input, keeping operator workload low, using a single crew member, and having lightning-fast deployment times.
But let's be crystal clear here. Above all the points and the heavy payloads, safety is absolutely paramount. During these intense flight paths, there are 500-foot hard geofence boundaries completely separating the active flight zones from the spectators over at NASA Ames. And if they cross it, any excursion past these boundaries results in instant, immediate disqualification. It proves without a doubt that these flyers must be just as safe as they are capable. So, as these teams engineer their way through those 1-mile ferries, manufactured tornadoes, and GPS-denied slaloms, when the dust finally settles at NASA Ames, after pushing the absolute limits of aviation and autonomy, we're left wondering which of these incredible machines will conquer these flight paths and truly become the future of emergency rescue. Thanks for joining me on this explainer, everyone. I really hope this helped you visualize the intense challenges ahead.